Hello, everyone. My name is Frederico, and I'm from the Federal University of Ouro Preto. And I'm going to introduce you deep learning based visual odometry models for mobile robotics. In our introduction, we're going to talk about what is odometry and the different ways to measure it. So, odometry is a common problem in navigation systems where we need to estimate a vehicle's position in a given environment. This can be useful to perform tests such as autonomous navigation and obstacle avoidance. So in these tests, you'll need to contain and preserve information about the vehicle's position and orientation in the space to avoid other robots or to perform other autonomous tasks and so on. Uh, there are different techniques and sensor types to measure odometry. We've got GPS, we got visual odometry that's done mostly through cameras. We got wheel odometry, laser odometry, and odometry through IMUs. So each of these techniques and sensor types, you can even fuse them to get better odometry, but they all have an associated cost, both computationally or financially. It can be expensive to fuse all this data to gather all the needed sensors to have a reliable odometry. So in this work, we're gonna measure mobile robots' odometry with only a monocular camera. And we're gonna do this through a deep learning based approach. So we train a neural network to relate an image to a given position on an environment. Uh, so we're gonna measure odometry in a domestic or industrial scenario where multiple robots will explore the same environment. We're gonna explain further our methodology, how this is gonna work. So for our references, the main two aspects of our reference are mobile robotics and edge AI. On the edge AI side, we've got Wang, Madzia, and Clippo all showing that we are every time more needing more processing uh, power at the edge in cases where you can't reach the cloud for processing these neural networks. While Quingley and Sid, they highlight the main advantages of using ROS, which is the Robot Operational System, to build mobile robots. So, for our methodology, we developed a robotic platform with SLAM capabilities, and SLAM is simultaneously location and mapping. This SLAM algorithm that we're going to use is going to feed the neural network that we're going to use, as we show here. So we propose a visual odometry approach using deep learning. So we trained a neural network to relate an image of the monocular camera, which the monocular camera we're going to capture, to a given position on this map that we mapped through a SLAM algorithm. And so here is our workflow where we're going to need a first robot equipped with a camera, a LiDAR sensor, and an IMU to map the domestic environment with a SLAM algorithm. So once we get this mapped this map that we obtain through navigating the environment with the robot, we teleoperate the robot through the environment. Then we build a data set relating the images and a position and orientation data from this lane algorithm. So this data is used to train a neural network to relate the images with a given position in this mapped environment. So this we do this to achieve multiple robots equipped with only a monocular camera can have an odometry inside this environment. So we collect this ground truth, fixing a starting point for the robot, and we teleoperate the robot through this domestic environment, and we get the data for the neural network. We're going to talk about some results that we got in this approach. So we evaluated three models according to an Euclidean distance between the prediction and the ground truth of our network. So as we can see, the ResNet 50 model had the better result, which is the the mean error the smallest mean error. And also we use a standard deviation to see if the errors are too different from each other. So this is the table where we show that the mean error of the ResNet model was 45 centimeters approximately. We also evaluate these models through a scatter plot where the blue points are the prediction points and the red points are the ground truth points. And this is our custom model scatter plot. This is the second VGG16 model. And this is the ResNet 50 model. We need in this approach to the blue points adjust right where the red points are. So if they are too apart, it means that they're not aligning too well and the regression is not quite working. So as the ResNet 15 model had the best results, we further evaluated to see if it was actually making sense. So we have an histogram of the ResNet model that shows that mostly of our errors are below the or mean error. We also have a box plot to see the distribution of our error, and it also shows us that we are below, most of our errors are below our mean errors. So to conclude this work, we presented an approach to visual odometry through deep learning techniques, where our best model, a ResNet 15 model, corresponds having an average error of 45 centimeters, which corresponds to 10% of the biggest distance on our environment, which is 4.5 meters. Thank you. This was our presentation.